Yes. Okay. Take it away.
Okay. Hi, everyone. I'm Wen, and I'll be talking today about robustness. Oh, I don't have to look into the camera, obviously. Anyway, hi, everyone. It's good to feel your presence across this YouTube channel. I'll be talking today about robustness as a refinement type, and that sort of like gets into machine learning and neural networks and verifying that neural networks are robust against adversarial examples by using refinement types. And so we'll get into like what all of those things mean separately and together like during this talk. But yeah, okay. So my name is Wen. This is joint work with Ekaterina Komenanskaya and Daniel Kienitz, done at the Lab for AI and Verification at Heriot-Watt University. Okay, so imagine you're me, and you're bored on a Monday night, a couple of days before you have to give a talk, and you decide to train a neural network to classify which of your friends have cats and which have dogs. So you ask some of your friends for pictures of their pets, and you put together a data set and let the neural network have a go. By the way, everyone, that cutie on the bottom right is my cat. Her name is Saza, and she is adorable. She's very brave, and she had to go to the kitty hospital the other day, but she seems to be recovering really well, so I'm really glad about that. Anyway, so we were training a neural network. So personally, like it was a couple of days before the talk, and I asked some friends. So I managed to get 4 pictures of 4 different pets. So I'd say that's a fair data set. But these images, they're pretty big. Like they're almost 500,000 pixels each. And I say pretty big, like as far as photos go, these are not even high res. But for like a neural network, 500,000 pixels translates to 500,000 inputs. So that is, whew, that's a lot. So you're more likely to present a neural network with something like this. Now that is just over 1,000 pixels per image, and it's not too bad. I still think we could do an all right job, like classifying these. Like, I'm not sure about Saucisse on the top left. Like, he could, I don't know, that could be like a little French bulldog, as far as I can tell. Like, I'm not even sure that's a cat anymore, but the rest, they're pretty obvious. Like, Oki is still very clearly a dog, and the other 2 lol buns are still very clearly cats. But we're humans, and it's way more fun to look at cute high-res pictures of pets. So we'll do that. So usually what you do is you would train a deep convolutional wordsing. Usually you would train a deep convolutional neural network, and you would hope that it would learn some salient features that can be used to tell cats from dogs, and then use those to classify them. But we've all got quality neural networks, so let's see if we can find some easy features to tell them apart. And usually this would be where there's some crowd interaction, but well, not all of you can give me direct feedback. Patrick, do you want to come on and have a go to tell me about a feature that I could use to differentiate cats from dogs here?
The big snout of the dog.
Right, so dogs have a big snout, and cats, well, they do not have a big snout. They have cute little snouts. Yeah, that would probably work. It's a rather complex feature, though. Like you would have to know what a snout is, and you'd have to be able to measure its size in multiple dimensions. I think I have a simpler one. If there's anything I know, it's that dogs love going for walks. So we're probably more likely to see a dog out and about in nature, and thus lots of green. And look, there's lots of green around Oki here. That's very good. But unfortunately, Saucisse also loves going out into nature, and so there's lots of green around him as well. But still, it's like we eliminated like 2 of the cats from the dog class with this, so that's not too bad, right? So maybe we just need to add a second feature. So one thing I noticed is that 2/3 of all cats have gray fur, but dogs never have gray fur. So we could use that, for instance. And then we could write down, for instance, that dogs, well, what does it mean what a dog is? Well, based on what we've seen so far, I feel fairly confident in saying that a dog is something with lots of green and very little gray. that I think really cuts the core of what it means to be a dog. So let's pick those and let's slap some axes on there. And would you look at that? They're already in the right places. It's like I planned this. Anyway, on the x-axis we have the inverse of grayness, so ungrayness. It's like I had to force it a little bit to make it work in this orientation. But so 0 means there's lots of gray, and 1 means there is basically no gray. And then on the y-axis we have greenness. So how much green there is in the picture, and this goes in the intuitive direction. So we have 0, which is no green, and we have 1, which is tons of green, just lots. Cool. Now let's abstract away a little bit, because technically those images correspond to just like the points on this plot, and them being really big is going to be a little bit confusing. So we've got this plot now. We've got that little floating dot there, which is Oki, which is our dog. And then on the axes, we have the 0, 0, 1, which is Saucisse, a cat. Then at 0, 0, we have Sparkles, a cat. And then on 1, 0, we have Zaza, also a cat. So now what we want to do is we want to find something which we want to find a line which we could use to separate these points. So we could, for instance, pick this line, just right there. Everything to the right of that line is a dog. And that works fine on all the dogs that we know of. But for instance, we have this point right here. We look at Oki, and we see that if we pick a point which is a tiny step away from Oki, that's already a cat. Now, mind you, we don't have any images that correspond to this point, and we can't visualize it. We can't be like, oh, well, show us what that point would look like, because we've reduced the complexity like a huge degree. All we know really is how green that point is and how ungray that point is. And we're working under the assumption that we've correctly identified the feature space of greenness and ungrayness in which cats are linearly separable from dogs. And I really think that's a good assumption, of course. So based on that assumption, if something is really close to a known dog in the feature space, it's probably still a dog. So we kind of want that one to be, well, a dog. So let's move the line a little bit. Oh, we moved it a lot. Right. OK, so now we have a different problem. So points that, for instance, are really close to Zaza are now classified as dog. Like, even the smallest bit of green could push Zaza into being classified as a dog now, which, frankly, like, if I put Zaza into a tiny green hat, I don't think that makes her a dog. Does that look like a dog to you? It does to the classifier. Right, so final move. We're putting the line smack dab in the middle of these points now. So if we take a small step from any known cat or known dog, the classification remains the same. So that is, one could say, robust. Cool, so what have we seen so far? Let's take stock. We've seen some basic concepts like data sets, features, and training networks, or finding like lines which separate all the points into the correct classes. Now, you can extract features manually, like we did with our own neural networks. Or you could have the hope that if you have a deep neural network, so a neural network with many layers, you could hope that the first few layers learn to isolate all the relevant features. And the last few layers, or even last layer, then performs classification based on those features. We've also seen that neural networks are sneaky bastards. They don't usually use the features that you'd expect them to use. They just use whatever features are easiest. And usually this shows up due to flaws in your data set. So for instance, here we had the accident that really the problem was that we had 4 images, right? So there were some problems with our data set. But for instance, I forget the name of the publication, but there is this publication where they show that a large classifier network trained on ImageNet, which is a fairly common benchmark, it had learned to identify horses by looking at a particular bit on the bottom left of the image where usually the watermark of the horse ranch was. So that is, yeah, they could obviously trick that network, not necessarily by putting a tiny hat on the horse, but like just take an image of a car and slap that watermark on, and the network is 100% sure that it's a horse. So you don't want that sort of stuff, especially in like safety critical situations where being able to trick the network would lead to a serious security problem. So we've also learned about adversarial examples here. So for instance, when I put a tiny green hat on my cat, and I can do that by drawing, but I could also do that in real life, just put a tiny green hat on her, if I happen to know that that would trick the algorithm, with a really minimal change. And also importantly, without changing how humans would classify her. So you are all not fooled, but the network was, and that's important. And also we've seen robustness to adversarial examples. And specifically here, we have measured robustness by measuring distance in the feature space. So things that are closely put together in the feature space are assumed to be in similar classes. Cool. What's still to come? Well, we've set the scene about like what we're doing here. We're classifying pets. It's important. So there is really 3 separate problems that we would be thinking about. The first one is our data good? Now, obviously, it wasn't. The second was, did we find the right features? In retrospect, I don't think we found the right features. And the last question is, the network that we found, is that network robust around these features? So the data science that I've done in this talk was terrible, of course. I hope you noticed that. And there's a reason for that, which is that we tend to think of verification more or less as a replacement for testing. You write down your specification and you prove that your program follows the specification and done. It's a good program. Now, I don't normally agree with that mindset, but it's especially harmful here. Verification is no replacement for good data science practices. It only helps you be sure that the function that you found follows your specification. And remember, you don't even always have a good, solid specification. So the specification, for instance, that we used here really was data dependent. So if our data is bad, then so is our specification. Now, there are cases in which you have solid specifications, but they are kind of rare. Cool. So in this talk, really, as you can tell, we're really only concerned with the last question. So if we have a network and we have a specification, can we automate some sort of test, some sort of formal proof, really, that our network is robust for this, robust around these features, or like adheres to the specification? And we're approaching this problem from PL. So we want to look for lightweight approaches to verifying these properties. And that brings us to robustness as a refinement type. We're going to do that by talking about the type of images whose features are within some distance of the features of a known cat, for instance, or of a known dog. Recall, the features here are extracted from data and by the neural networks. And neural networks are fairly constrained functions. They're all sequences of linear functions alternated with nonlinear activation functions, which are drawn from a highly limited set. That's like if you pick 3, you cover most of the neural networks, essentially. Cool. So just a brief reminder for everyone here, what is a refinement type? So a refinement type is a type refined with an SMT-checkable predicate. So for instance, the first line here says we have the type of R+, the positive real numbers, and that is the type of real numbers refined with the checkable predicate that that number is bigger or equal to 0. Okay, so that's not positive, is it? That's positive or 0. Well, whatever. You understand what I mean. Then on the second line, we see the number 4, which is in fact a positive real number. And then as a second example, we have the type of vectors. So vectors are lists with a certain length. So here it's defined as the type of lists where the length is exactly n. And as an example here, we have the list of 1/2 and 1. And that is a vector of with length 2. And you'll notice that the predicates that we attach to those types have are in no way reflected in the term language. So really, these are sent off to a solver, and we don't have to put effort into materializing a proof for these claims. So they're lightweight in that sense, that we don't have to be bothered by giving the proofs. As you might be able to tell or not, I'm not sure, this slide is in F star. So F star has a very tight integration with Z3, which is like one of the standard SMT solvers. All F star programs can be translated to Z3 programs in some way or another, which means that if we write a framework for neural nets in F star, it can run on Z3, and therefore Z3 will be able to answer us simple questions about the network. So we wrote a library called StarChild in F star. We also wrote a similar library in Liquid Haskell, which is Haskell extended with refinement types. But because the syntax of StarChild is a little bit nicer, specifically the syntax for refinement types in F star is a little bit more compact. We'll be focusing mostly on the F star work here, but I will be mentioning the Liquid Haskell work occasionally. OK, so let's get back to our example and get ourselves a classifier for our pet problem. So the architecture we're going with is very simple. It has two inputs, x1 and x2, or greenness and ungrayness. It's a very, very natural word, I know. And it computes the linear function on the right-hand side. So multiplies them by their respective weights, adds them up, and then, oh, that should be adds the bias. And then adds the bias. It just happens that the bias that I'm about to pick on the next slide is negative. So I think I left that minus in there. And then after it computes that linear function, it applies a nonlinear activation function f. So let's find the model. This is a model. So we've picked 1/2 for both of the weights and minus 0.9. You can see where the minus came from now. Minus 0.9 for the bias. And for our activation function, we have chosen the threshold function, which is simply the function that returns 1 if a thing is bigger than 0 or equal to it, and 0 otherwise. Now, this is a real bad function to use in machine learning because it's very not differentiable, but it is very intuitive. And we're not going to be differentiating things in this talk anyway. So let's just briefly check using our heads. 1/2 plus 1/2 equals 1. And 1 minus 0.9 is 0.1, which would give us 1. So if the inputs are both 1, then the output is 1. So Oki is still a dog. And we could do similar checks and find that all the cats are still cats, according to this neural network. Cool. So this is the whole thing that we've just seen essentially lifted up and put into F star. So we've got a network defined by a matrix of weights and a list of biases. And then we have our classify function again, which just says run that model. And that just calls into a library that does some basic neural network implementation. Specifically, like it does all the correct matrix multiplications, and it maps that constructor threshold to the actual threshold function. So that's what it would look like in F star. This is mostly relevant for the next slide, which is where we're going to write down our specification. So remember that we were taking tiny steps from our known dog, and we have to say, how big a tiny step do we want to take? So we want to take an epsilon size step. And epsilon here we pick to be 0.1. Then we define a function called doggy. And what that means is this input characteristic of dogs? Now, it just so happens that the ranges for both ungrayness and greenness coincide, kind of like I planned it that way. So the greenness for dogs is when it's around 1, like within an epsilon step of 1, and the ungrayness is also a dog if it's around 1. And then we can write our specification. So we have a function. We don't bother giving it a name because it's already named. It's called classify. But yeah, we have a function which takes 2 inputs and gives 1 output. And we refine this function type with is input 1 and input 2, are they both in expected ranges for doggies? So if both of the inputs are in the expected ranges for doggies, then we expect the thing to be classified as a doggy. And we can write this code. That's really all we need to write. And then when we type check our program, F* compiles all this stuff down to Z3, and it emits some Z3 Lisp stuff, and which you can see here in an idealized manner. And then Z3 replies sat. Yes, this is correct. This network is robust around doggies. Good job. So concluding our example, that works. But does it work? Like, clearly, the example we've been working with works, but it's not incredibly representative of neural networks out there in the real world. Like, it's only got 2 inputs. It's only got 1 layer, and nobody uses the threshold function. So does our approach really scale, and what sort of problems do we encounter? So there's really 3 main issues that we encounter. Some of you might have been able to predict the first one for sure. Solvers, SMT solvers specifically, they don't do nonlinear arithmetic. That is to say, SMT-lib2 as a format for SMT solvers supports something called nonlinear real arithmetic, but that just means that you can use multiplication however you want. So it's a tiny subset of nonlinear arithmetic, and there's nothing about exponentials or logarithms or trigonometric functions. And of course, the logics that include these things are wildly undecidable, so it is expected that they wouldn't support those. Now, secondly, integration with F* actually introduces a significant slowdown. So yeah, we'll get to that in a second, but the Z3 that I showed you was extremely idealized in that the F* generated Z3 code would not have fit on one slide or even in this entire presentation. And the slowdown looks like an exponential factor levels of significance, so it's not great. And lastly, SMT solvers don't really scale to realistic sizes of neural networks. So like I mentioned at the start, working with even a moderate resolution of image can result in like 500,000 of inputs. And obviously, that's a little bit like helped by taking a convolutional neural network. But still, like these things tend to be quite large. And that scales quite poorly. Not to mention that these things, so Z3 obviously doesn't scale to like 500,000 variables in a query. But also it scales quite poorly with the number of layers. Since SMT queries don't really have like a concept of abstraction, all definitions are just blindly inlined, essentially. So there were function definitions in the query I showed you earlier, if you picked up on that, but those are just inlined immediately everywhere. And so, for instance, a node in the first hidden layer would depend on all the inputs of the network. But a node in the second hidden layer would depend on all the nodes in the first hidden layer, all of which depend on all the inputs. So you can see how this would escalate fairly quickly, especially once the networks get deeper and deeper and wider. So yeah, so the solvers don't really tend to scale. So discussing these things one by one quickly. Solvers don't do nonlinear arithmetic. So we can solve this. We can make our activation functions linear. Now, obviously, there's no like easy way to just say like, oh, this nonlinear function is now linear. But yeah, there's actually, so what we do as an extremely simple approach is we just approximate our activation functions with a bunch of lines. So we have here 3 functions. All of them are the sigmoid activation function. And we approximate them with 1, 5, and 25 evenly spaced line segments. There's actually quite a lot of precedent for doing stuff like this. So for instance, the ReLU activation function is already piecewise linear. That's like 2 lines, one coming in horizontally, and then a second line going back out. So it's quite common to take piecewise linear approximations of activation functions also when implementing neural networks on hardware, because there you have to discretize these things. Yeah, so that's how we make our functions linear. And that is a quite naive approach. Like, for instance, you can see that in the first plot, it might be a much better function to really like tilt it a little bit more and make the range over which it goes a little bit smaller. But that wouldn't be evenly spaced. Now we have more interesting algorithms for making these piecewise linear activation functions, but really, after doing some experiments, it seems that like as long as n is larger than 3, it really works quite well. So what you see here is a graph that says we're training with the nonlinear h-stand function, and then when we run the network with the linear approximation, we show here the loss in test accuracy. And as you see, after 3, the loss in accuracy is completely negligible. So yeah, I mean, we could do more subtle things, but really, this already works really well. Surprisingly, really. Point 2. Integration with F* introduces a significant slowdown. So here we see a fun graph, which got a fun exponential in there. So yeah, this graph measures the verification time for our pet classifier, generalized to n features. And if you can't find the curve for Z3, it's because it never goes over 1. So F* encodes the entire program in Z3, including definitions, which means that in the worst case, Z3, which is an engine for equational reasoning, is tasked with performing reduction, which is really bad. And you may notice that the different curves for StarChild are labeled here with assert and assert norm. And that is because with careful use of the specific assert norm construct, you can force F* to do normalization before encoding the program to Z3. So that takes like a huge chunk out of that curve, but it still doesn't make it any less exponential looking, or at least any less dire. Mind you, I don't have any evidence that any of these curves are precisely exponential, or that the Z3 curve doesn't go like exponential right across the 300 boundary. This is just a measurement, really. Yeah, so the problem here seems to be that F* tries to do a very general encoding. And we can really clearly get good results if we formulate our queries carefully, which you can see here by the Z3 curve. So the plan is to move away from F* and from these generic encodings into more neural network specific encodings to make to knock out this exponential factor and make queries a lot more efficient. But to do that, we'll probably have to drop like generality and make it specifically tethered to neural networks. And finally, the last point is that solvers, and by this I mean SMT solvers, don't scale to realistic sizes. So don't let the graph that I showed you just now fool you. Like, those networks were all extremely shallow, and they map directly from n to 1 outputs. From n inputs to 1 output. And once you start getting any more complex, Z3 starts scaling very, very poorly. And that's probably in part because Z3, I mean, it's obviously because it's a very difficult problem, but it's worsened by the fact that Z3 tries to solve a much, much more general problem than we need, really. And in doing so, it ignores tons of structure. And there are lots of solvers out there which fit our domain much better. So honorable mentions go out to Metitarsky, which adds in support for exponential functions. Unfortunately, the documentation for Metitarsky mentions that past 9 variables, there's no chance of ever getting an answer. So we don't really expect that one to really work well for us, but it's still a very impressive solver. Then we have the wonderfully named NNNM, which efficiently verifies ReLU neural networks. And ReLUs happen to be one of the most popular choices of activation functions, although that's a bit fraught since we don't really know why they work so well. And some recent work seems to indicate that they are particularly vulnerable to adversarial examples. And Marabou started out also as a solver specifically for ReLU networks, but is now generalized to handle networks with any piecewise linear functions. So Marabou really fits our use cases very well. Unfortunately, none of these are integrated with F-star, obviously, because they're research solvers, and F-star is very specifically tied to Z3. And given the support for real number arithmetic in F-star, which you can ask questions about, I don't think that many people actually use refinement types with real numbers in F-star. Also in Liquid Haskell, actually, like by just using real number arithmetic in both languages, I exposed a ton of bugs while implementing this. So we will likely have to come up with our own integration for these solvers, but that's okay, because fortunately, we were already planning to do that anyway because of the previous problem. OK, so to wrap up, I talked about robustness as a refinement type. So what we bring to the table here is that we're encoding robustness and really arbitrary verification conditions on neural networks. But robustness is a very common one. So we're encoding robustness as a refinement type. And we're currently leveraging existing integration with solvers to do this very easily. And get very lightweight verification of robustness or other verification conditions. But at the moment, we still need to improve integration with solvers. So we're kind of going to have to write our own. And we need a lot more flexibility in choosing solvers. And in light of that, I'm currently working on an extension of Agda, which can link up with Marabou and generate very efficient queries. And that's all for me. I will gladly take some questions.
Thank you, Wayne. Yes, applause for a very nice talk with a lot of really nice pictures and very good explanations of how data science works. So if you have access to Slido, you can read the questions yourself. Otherwise,
there's some questions that popped up.
Yeah.
Right. Orestes asks, to overcome issues of scale, have you considered moving to probabilistic satisfiability, i.e. use the neural network trick on deciding neural network properties themselves? No, but that sounds interesting. Work on explainable classifiers tries to find simple classifiers close to those thrown up by neural networks. So I'm not entirely sure what line of work you're referring to there, but so one thing that we have done is a dimensionality reduction, which tries to simplify the data. But also a thing that people do quite often is, say, they take a very complex network, and then they take a very simple architecture, and then they train them side by side so that the smaller network essentially learns to mimic or approximate the bigger one. And then we can verify the smaller network. So yes, like student-teacher models like that. Yeah, we are also looking into that. But it would have to work for a network of the size of a student model first to do that. So Thomas asks, have you looked at solvers such as DReal, which give delta complete results but may scale better? No. And I will just copy that into Google and look at that after the talk, because that sounds very interesting. Thanks, Thomas. Are there any further questions?
So there are a couple of people have joined. If they want to ask questions, they can just go ahead and ask directly. Otherwise, if they don't want to ask directly, then I would say let's thank Wen and Jesse again for these very nice talks.